Good morning. I want to thank you for taking a little bit of your time to listen to this video. I will be talking about a project developed with the participation of several research units in Portugal. With this project, we have the objective of developing a detector to enable the radiobiology professionals to perform their measurements with good spatial resolution and real-time dose measurements. For radiotherapy sessions, it is important to know how cells and organs react to radiation. This is the objective of an area called radiobiology, where cells, tissues, or even small animals are irradiated, and the consequences of this irradiation are studied. As I said, there is very important information extracted from radiobiology studies. The first is the cell survival curve, which shows the fraction of cells in a given population that is able to survive the absorption of a given radiation dose. The cell survival against dose is graphically represented by plotting the surviving fraction on a log scale against the dose. Other main factor studied by radiobiology is the relative biological effectiveness. And the relative biological effectiveness compares the dose of a given test radiation to the dose of a standard radiation needed to produce the same biological effect. The relative biological effectiveness is a complex thing to study because it depends on many factors like the dose rate, and the linear energy transfer, which is the average energy deposited per unit path length along the track of an ionizing particle. It is already known that it is possible to have a different relative biological effectiveness for particles with the same linear energy transfer, depending on the track structure of the particle. And so, to study the biological effects of radiation, it is important to have a dose distribution map at the micrometric scale. Having this in mind, this need for a dose map at the micrometric scale, we aim at developing a detector that offers real-time dose measurements, good spatial resolution, and tissue equivalence. In this project, we are working with a couple of biologists that will help us explore the possibility of attaching the cell culture directly on top of the detector's sensitive area. With this technique, we expect to eliminate the errors produced by the cell culture plates. In the first iteration, we will be using skin cell cultures. And skin cells are interesting because of two facts. First, when a microbeam is used, the dose absorbed by the skin is non-negligible. And second, because the literature shows that it is not easy to measure the dose transferred to skin. This detector will be developed using scintillating optical fibers, taking advantage of the fiber's small size. The optical fibers will be placed side by side, describing this way a plane. The possibility of having two orthogonal planes will also be studied. And using the two orthogonal planes, it is possible to have a measurement of the dose delivered to a point. The detector's spatial resolution will be a function of the optical fiber's dimensions. And we are planning to work with optical fibers of 1 millimeter, half a millimeter, and a quarter of a millimeter. Developing a detector of this type involves many steps, and all of them are described in this poster. We had to test the photodetector and the data acquisition board, we had to study the crosstalk between optical fibers, and we had to study and determine the best way to assemble the optical fiber array and to control its quality. The detector was designed, and finally, the simulations studying the detector's shielding and optical photon transport were performed.